Okay, hello everyone. It's Monday, March 22nd. It's day 24 of our lectures. So let us start. I recall you have your exam on Friday. It will be again in Zoom like usual, like we had your optional quiz last Friday. So please make sure you attend. Please be with your cameras and please spend the time left to get prepared. It's serious. So I recall, if you don't remember chapter 3, and some of you unfortunately, yes, if you don't remember, if you forgot how to use property tables, it's still backbone for the entire course, so please focus on this. If you know how to do it, please focus on chapter 4 and 5. I recall your homework 5 is due Wednesday. Please do it. Today and tomorrow we still have TA help sessions from 5 to 7. And on Wednesday, if you need me, it will be my help session to prepare for your exam. I will not give extra lecture because last Friday I recorded and we had like summary lecture for exam 2, but I will be able to help. So please take it seriously. Okay? It's important. But now, to avoid wasting time, even exam 2 will be based on chapter 4 and 5. Now we are starting new topic today and on Wednesday. And this is, let me share my screen. This is, we will be talking about second law of thermodynamics. And this is something you must eventually to pick up. Okay, please understand it's something important we'll be talking about. So what is second law? And today, so this is something we will be talking about from now and until as the end of the course. And this is something that really makes you different from ancient Greeks. Remember, I told you at first lecture, ancient Greeks did not know how to convert heat into work. Ancient Greeks did not know how to transfer heat from cold to hot source. You know this. It's different. It makes you different. But still there is something. It's not easy to understand because ancient Greeks were clever, right? So since they did not know something what you know, it is serious and you should pick this up. What is second law? And there will be big philosophy behind this. It will be less formulas, but big philosophy, big theory. So please listen to me. Lectures will be recorded. You can hear it. You can ask a question, but this is something that I want you to understand. Okay? This is something that makes a difference. So what is second law? It's not easy to answer in one word. So it will be several approaches how we'll do it. But key point is the following, that in addition to energy conservation, there is something that rules the nature. And there are this something, there are at least 10 formulations. There are different ways to how to explain it. And nobody can prove it experimentally. But believe me, if this was wrong, then Big Bang would not happen, our universe would not exist, and we would not be here. So that is something that is true. And that's something that you should understand. So let me explain, let's start approaching like this. So what is second law and how it works? So remember, for instance, when you were in chapter 4 and chapter 5, for instance, what was typical task? I told you, okay, there is piston cylinder assembly, or there is a turbine with inlet and outlet, right? I told you, here is state 1, here is state 2, here are parameters, and please find delta U, please find work output, and you did it, right? And when you did it, you assume this turbine exists, right? You did not have a question about this. You assume it exists and you solved it, right? Well, of course, if the answer was ridiculous, if you had negative temperature in Kelvin scale and negative pressure, that something was wrong. But if the answer was suitable, you assume it's correct. Yes? The problem is, however, that many of these examples, many of student problems from your textbook in chapter 1 to 5, don't exist in practice. They may not exist. Okay? They may not exist not because you don't know how to make it, but because of second law. And until now, it was not your problem. It was not your business if they exist or not. I just gave you a task and you solved it. Now, since chapter 6, it's your business. It's your assignment. It's your task to understand, does this turbine exist or not? Does it obey second law or not? Okay. It is your task to understand if it may exist or not. That's what I'm going to teach you how to do it. Another point that most of the processes we have, they go in one direction. For instance, if I just have a hot cup of coffee in my room and I will release it here, what will happen? Coffee will get colder. True? It's looks like impossible that this coffee will eventually be boiled and room will be colder, because this process goes to equilibrium. This process goes in one direction. You know, when you see electric lamp, why we have lights there? Because there is electric current which goes through a wire. Wire heats it, right? And then when the wire is heated, it produces light. But it's impossible to do vice versa. If I just heat a wire by a candle, there will be no light. There will be no current there, right? If I have this cup of coffee and I put inside brick of sugar, the sugar will be dissolved and I will have sweet coffee. But it's not easy to get it back, right? At least not straightforward. Potentially, after some chemical transformation, I can get this brick of sugar, but it's not straightforward. So this process go in one direction. They go towards equilibrium. It's illustration. And that's why our universe goes from Big Bang. Our universe goes from Big Bang to the thermal death of universe, not vice versa. We are first born and then die, not vice versa. We go in one direction. We get elder, but we cannot get young. Because all the time we generate entropy and we cannot destroy it. That is how it works. So that's second law describes the direction of the process made in if it may happen or not. Okay. And to describe it, let me say something like this. Let's forget about physics and let's talk about some illustration, for instance, right? So basically, if you talk about laws, what kind of laws we have? You agree you have like physical laws, right? What are physical laws, for example? It's like F is equal to ma, right? It's physical law, correct? Newton's law. Or it stays at gravity law, right? That all bodies are attracting. Or you know that that positive and negative charge are attracting and the charge of one sign are contracting. That's all physical laws, right? But if it were, what we know about physical laws? Can they be violated? Can you change it? Can you violate Newton's law? Can you violate energy conservation? I believe not. You cannot. And that's make different from what? From what we call juridical laws, right? What are juridical laws? If you tell you, well, starting from, let's say, religious books like Bible or Quran or whatever, and ending with Constitution or Criminal Codex, what they tell you? Like, don't kill, don't steal, don't rob, don't cheat your partner, your spouse, or your country, don't hit somebody, don't abuse, don't discriminate, don't harass. Right? Why do they say it? Because potentially you can do it, right? And there is some police officer or like some moral statement that enforce you don't do it. You can kill, you can cheat, you can abuse. And that's why it says you don't do it, don't violate. These statements which create any community because there are policies that you should not limitate. You should violate. There are some limitations, right? So that's a difference. You cannot violate physical laws, but you can violate juridical laws, right? So second law of thermodynamics, it's something in between them, okay? Why? You cannot violate it, but I will explain why. Because it shows the penalty you pay for some violations. Okay? To understand and to describe, let me do like this. Let me explain like this. And this, first of all, let's forget about ancient Greeks. Let's talk about the natural environment, but it's the same story. For instance, when you are children, somebody tell you do something you don't do, you just follow, right? When my kid is 6 years old, when he was very small, I told him, don't go on red light, don't eat ice cream, a lot of ice cream, don't do something, go to school or whatever, right? And when you are small, you follow it. But when you will get a little bit elder, you start doubting and you start asking questions, correct? And my son asked me, so why shouldn't I eat ice cream? And somehow you should explain this, right? I tell him, if you will eat ice cream, you will get cold. If you don't go to school, you will not be educated and you will not find a job. If you go on red light, eventually, like, you can be hit by a car. If you will kill somebody, somebody will kill you. So it will be some consequences. So you tell people that, okay, you want to violate the statements, you want to harass somebody, okay, do it, but there will be some penalty, you will be punished. And in fact, in our adult life, that mostly happens. We all do something bad, right? We eat unhealthy food, we behave unhealthy, and doctor tell you, okay, you want to do something, but it will be consequence. It will be high blood pressure, high sugar level, maybe something worse. It's penalty you pay. Something the penalty is clearly seen. Sometimes it's just probable penalty, but that's what happened, right? So that is the difference between kids and adult people. Adult people know what is the consequence and how you will be punished. Correct? Why I say about these trivial things? Because assume that ancient Greeks were like children in terms of civilization. They are very smart, but they did not know something that we know. And if it was Aristotle or Socrates or Plato who gave this lecture, this guy would be very smart. But he would tell you, it's impossible to transfer heat from cold to source. If it was summertime now, he would tell you how to cool something. Wait until winter or go to Mount Olympus and bring ice from there. He thought that otherwise it's impossible. He had no idea about refrigerator that all of us have. Or if he would see a vessel with hot steam, he would not understand that you can rotate a wheel. He would tell you, if you want to do some manufacturing, okay, you need slaves, you need horses, you need elephants, you need some mechanical effort. He had no idea it can be done by steam, right? But we know this. In fact, what we do is like this. But do you understand that when you do anything like this, you make a step towards thermal death of nature because you destroy quality of energy. When you ride a car, you spend gasoline. You burn gasoline, you burn oil, and you cannot get it back, right? So let's look like this. Imagine that the god or the nature told ancient Greeks, don't convert heat into work. Don't transfer heat from cold to hot source. And they say, okay, yes, I will follow. But when the god or the nature, and according to Einstein, it's the same, told us, do it, you say, I'm sorry, but that's how our civilization is based on. That is what we do every day. We do transfer heat from cold to hot source. We do convert heat into work. True? That's how our transportation industry and everything is based on. And the god or nature told you, don't do it. I don't want this because you will never get it back. Because you will spend your gasoline and eventually will not have it. All these items that you do, it's one step towards thermal death of universe. Because you generate entropy. And you reply, well, I'm sorry, but that's how we live. That's what we do. Okay? And the god or nature replies to you, okay, then do whatever you do. Do whatever you want. But there will be penalty for this. There will be policy and there will be penalty you pay. You cannot avoid it. Do you understand this? So second law of thermodynamics tell you what penalty you pay. Okay? And the currency, the money in which you pay this penalty, we call entropy, not enthalpy, entropy. Character S. We'll talk about entropy in chapter 7. It states that when you do anything like this, in the most of the process we do in our life, you generate entropy, which you cannot destroy. It's like when you get penalty ticket for driving. Unlike our class, you cannot get bonus ticket for driving, right? If you have penalty ticket, you cannot avoid it. If you don't pay, if you give a bribe to police officer, or if you kill police officer, you will get extra penalty. Eventually, you will end up in a jail. You will increase the crime. You cannot get rid of it. The same story for entropy. You cannot avoid second law. You should follow it. Does it make sense? Do you understand? Please ask me something. So that's philosophical concept. There are at least 10 formulations of second law, which tells you, the second law tells you what is the direction of the process, in which direction you go, and how to proceed. It is second law which tells you that there was first Big Bang, and then universe is expanding, and not vice versa, that you cannot go to the past. It is second law that tells you that you are born, and then you are young, and then you get elder. You cannot be younger. You can never get younger, because to get younger, you should destroy entropy. You should destroy your penalty ticket, which is impossible. Does it make sense? I know it's more philosophy than physics, but it's something that you should pick up. It will be hard at the very beginning, but when you understand it, everything will be qualified and quantified, and you will understand it. And you know why I talk about ancient Greeks so much? Again, ancient Greeks had no idea about thermodynamics, but they were smart. And for instance, if you remember the ancient philosophers, there was a philosopher named Heraclitus. So what he told? That the world should be in order. Everything should be ordered. And when something appears, it's a violation of the order. So when you are born, when animal is born, when insect is born, when plant is born and appears, you violate the order. And you should be punished for this. And how you can be punished? The only reasonable punishment is death. It's death execution. So everything which is born should die. That's how he told. So everything that appeared after the world was created should die. And first you are born, then you are die, not vice versa. Correct? Because you go from past to future. So it's philosophy. But is it not a second law? It is. That is a second law. That is how it looks like. That is your second law. So that's what we are going to understand and quantify now. Does it make sense? So it is second. So in addition to first law of thermodynamics, in addition to energy conservation, there is something else that rules the nature. And that is what we are starting talking about. Do you understand? For instance, like in the process that I considered here, imagine that it goes vice versa. Imagine that my coffee will get hotter and room get colder. Imagine that I hit a wire and the current will go here. Would this violate first law? No, because it does not violate energy conservation. But it does not happen because there is something else that ancient Greeks did not know, but we know. It's second law. So that it is. And now I will come back to actually to nature, right? From philosophy. So second law tells it's a guiding principle of whether a process can occur or not. And there are many aspects of second law that we are going to describe. So it will predict the direction of the process. And in that way, it establishes conditions of equilibrium. So what does it mean? Remember, if you release a system, if you have fully isolated system, the system will eventually remain in equilibrium. So the process goes towards equilibrium, right? Also, later we'll quantify, we'll determine the best theoretical performance of cycles, efficiency and performance of cycles, of engines, and so forth. And it will be what? And it will be also realized that, remember, when we talk about thermal efficiency, we discussed that it's not 100%, right? Because you lose something. When we saw desired or required, it was not 100%. And I ask you why, and we discuss it because you always have dissipation, because all devices are not ideal, because you always have losses. Okay, that's true, but not because of this now. This tells you that it's not because you don't know how to do it, but there is theoretical maximum that you can attain because of the second law. Because if this was wrong, then our nature would not exist. Do you understand? That's how our nature is ruled. And here I don't want like to talk about religious aspects. Some people can believe and can be abused, but in fact it doesn't violate. I can say that second law fully in line with the God and religion, because it may say like this. So when the world was created, when the God created the world, it was violation of second law actually, right? Because it was house and became something ordered. But everything which has happened after this, it goes towards thermal death of the universe. So which means that the God is a substance. It's some creature that may violate second law. The God can violate second law, but nobody else. That makes us different from the God. No person, no substance, nobody else can violate second law. We all should follow second law. Is it like understandable? Does it make sense? I believe so. So that it is. And later we'll quantify. So what is the best performance according to second law? And moreover, remember, we'll define a temperature scale independent of the properties, which we call temperature scale, Kelvin scale. So remember what is Kelvin scale. Kelvin scale is calculated, it states that there is absolute zero and calculates temperature from absolute zero, right? And you know that what is Kelvin, it's minus 273 Celsius, right? But why we call it Kelvin? Because it was George Thomson named for this Lord Kelvin who invented the scale, right? But believe me, Lord Kelvin, and that's we named it after him. But believe me, Lord Kelvin did not know that it's 2 minus 273 degrees. He did not know this number. What he knew, he came to this idea about absolute zero from second law. So based on second law, he understood, he invented that there is some temperature scale, and so, which will be like this, which will be independent of properties of a substance. He came to this point based on second law, and then he calculated how big is it. Do you understand this? So that's what we are talking. Now, there is one more way, and it's very good illustration here that second law is important, but it's secondary, while first law, energy conservation, is primary. So basically, here it is. It's really explained here through like electric circuit, consecutive electric circuit. So you should connect both of them to work. So if energy conservation works, then you should check second law. But if you violate first law, if there is no energy conservation in your system, in your hypothetical system, it means that it does not exist and no reason to check second law. Second law can show you anything. Second law, it's secondary after the primary first law. Does it make sense? Okay. Well, and as I told you, there are many alternative formulations, but we'll talk here about three of them: Clausius, Kelvin-Plank, and entropy statement. About entropy, we'll talk in next chapter, in chapter 7. But in chapter 6, we talk about Clausius and Kelvin-Plank. And you may understand what it is about. Because, like I recall, what makes us different from ancient Greeks? So we know that you can transfer heat from cold to hot source. Fridge does it. So we know there is a refrigeration cycle. So Clausius statement, it will be some statement about refrigeration cycle. It will give you some limitation on it. Does it make sense? And another point, that we know how to transfer heat into work, how to convert heat into work, unlike Greeks. So Kelvin-Planck statement will be statement about this transformation and some limitation about it. That's what we will do. Does it make sense? Please ask me something at this point if it's not easy for you. I know it's not easy, it's philosophy, but you should pick this up if you want to pass this course properly. It's still very important. Okay? Let's continue. No questions now? Okay. So, a couple of more concepts. Let's introduce the concept of, if you don't know yet, about thermal reservoir. So what is thermal reservoir? Thermal reservoir, it's some item, some body, which is so big that you may assume its temperature is fixed and does not change when it interacts with this body. It can be a lake, or atmosphere, or ocean, or a really big substance that you may assume that, okay, it has fixed temperature and it does not change. So when you come in touch with it, you interact with that temperature. And that's what we call reservoir. And typically we talk about two types of reservoirs. They are source and sink. Or sometimes we call it hot source and cold source. It's also possible. So what is it? What does it mean? So source or hot source, it's when you get it's something that has higher temperature than your temperature, so you take heat from it and use it somehow, right? Like you take heat from sun, or you take heat from like furnace, or you take heat from baking device, something like that, or from heater, whatever. And also there is a concept of sink. It's something when you release heat. If you open the window, if the room is very hot and you want to release this heat, you open the window and heat goes out. That is what we call cold reservoir or sink. Okay? Does it make sense? So then let's come to Kelvin-Planck statement of the second law. It's here. There are many ways how you can write it in Word, but it stated that it's impossible for any system to operate in a thermodynamic cycle and deliver a net amount of energy by work to its surrounding while receiving energy by heat transfer from a single reservoir. I don't request you to remember word by word, but I want to understand it in detail. So it states here that it's impossible to operate in such a manner that heat will entirely be converted into work. Okay? You should have another reservoir here to lose piece of this heat. That is the penalty you pay. Okay? It's a penalty you pay. It's not because you don't know how to do it. It's because of second law. It's Kelvin-Planck formulation. So if it was ancient Greek here, and I would show him what I'm doing here, I convert mechanical work into heat. But he would tell you cannot do vice versa. You cannot convert this heat into work. We know we can do it. But the God or the nature tell you, okay, you cannot convert entirely. You cannot convert each joule of energy. You can convert only 80% or 70% or 20%, how much we'll talk later. But something should be lost. That is a penalty. That is a tax I take from you for this. Because I don't want you to do this. Because it's against me, against nature. Because that's step towards thermal death of the universe. But we do it. And we pay this penalty. Does it make sense? Otherwise, it stays like this. That heat engine cannot have efficiency of 100%. So what is heat? At this point, let me recall if I don't remember if I introduced what is heat engine. Heat engine is not just, it's not necessarily engine. Heat engine, it's any device, okay? Any device which convert heat into work. Real in car engine also does it. You burn gasoline and convert it into rotating shaft and transportation. But that any device which does like this, any device which converts heat into work, and like any power cycle, it's heat engine. And what you know now, so that heat engine cannot do like you see here. It's impossible to convert everything into work. You should lose something. This QL, how we write it here, cannot be zero. You should pay some penalty. And later we will formulate what is the maximal penalty, what is the minimal penalty you pay. Do you understand? Otherwise, you can say like this, that if you have one thermal reservoir, your net work of a cycle can never be positive. It's like this. Well, it can be negative or zero. When it's zero? It's zero when your cycle is completely reversible, when you can go back and forward. Then zero is zero. But if it's not zero but negative, your system is not reversible, because then negative will become positive if you go clockwise and counterclockwise. Remember that work in opposite direction should be negative, so it will become positive if you do vice versa, which is impossible. So otherwise you cannot be younger. You cannot go from future to past. I recall heat engines, not necessarily engine. So what is heat engine? It's any device that receives heat from high temperature source, let it be sun or furnace or whatever. It converts part, not entirely, but part of this heat into work. That's what you want to get it. but releases reject the remaining heat into low temperature sink, and this is unavoidable. It operates over a cycle like this. Do you see? So that it is. So as you may see it, like I say, I can convert now mechanical work into heat. But if I have hot hands, it's not easy to shake it back. If I rotate here, I have stirring device here. If I rotate it in stir water by this pedal wheel, I will create hot, I will heat it, and heat will go out. But if I hit this device, my shaft will not rotate, not straightforward. So it's not easy to do it straightforward. You need to lose some heat. And it's not because you don't know how to do it. It's because of the second law. Please realize it. Does it make sense? Please ask me something at this point. No questions, I don't believe. Everybody understood everything or nobody understood nothing. What is closer? In between? Okay. So, just class, what we have typically in our life, so it's power plant. It's power cycle, that is classical heat engine. So remember what you see here, we did consider in the past. Turbines, boilers, condenser, each device we used to consider in chapter 5. You are still doing this homework. So it's inlet and outlet. You have inlet state 1, outlet state 2, and something in between them. Now what you see, they're connected. And that's how classical power device look like. So basically what we may have, typically, we may have a boiler. So what you see in power in this device, what we actually have here, we convert heat which comes in. Let's say you have a furnace, you have some kind of steam machine, you have a boiler, and this heat goes in. And you convert this heat into work. So how it works? So let's say here I have boiler. So my furnace, I boil my working fluid and I create a steam. So when I boil it, what does it mean? That I increase its enthalpy. My enthalpy is high now, right? And I come to a turbine. So remember how turbine does. My turbine produces work output. That's what I need from my turbine. So I will spend enthalpy here. Enthalpy at the outlet will be less than in the inlet, and the difference will be converted into work output. Remember? Trust we did it last week. Okay, that's how it is. But the key point, these two devices, boiler and turbine, they are crucial, but they not just have everything. Because what happened next? Next, you should have some kind of condenser. What happened in condenser? In condenser, it condensates. So your latent energy goes to environment. So you lose some heat here. And then you have a pump which goes back, compress substance outlet here to here, and then you boil it again. Definitely, so in pump you deposit work, so this work is negative from the point of view of the system, but work of the turbine is positive. So basically, if you look here, what will be? This is net work over your system, and since you go clockwise here, remember you go clockwise, work output will be positive because it's work done by the system. It's done by the system, not on the system, right? Because that's your power source of power plant, of power cycle, convert heat into work. For refrigeration, it will be boiler and condenser will be vice versa. Here go clockwise, so work output is positive. Correct? But key point here, that you cannot avoid this. Okay? Not because you don't know how to do it, because it's impossible, because otherwise you would not be here. Otherwise, our universe would not exist. It's second law. It's something that should happen. It's Kelvin-Plank statement of the second law. So what is efficiency? What is it? Remember how we introduced thermal efficiency in chapter 2. It's something, it's whatever you deal with, it's efficiency or performance, it's what is desired over required. From each device you want something and you need something, right? So if you look at heat engine, any kind of heat engine, what do you want from it? What you desire from your heat engine? From your heat engine, you desire work output, right? What do you require? You require heat input, right? Because you convert what you do in heat engine, you convert heat into work, correct? So what is thermal efficiency? Here it is. So you have these two equations which you solve. Again, like usually, you have two equations and four variables. So if you know two of them, you will find two others. So your thermal efficiency is nothing like this. And this value will be less than 100%. It's less than 1. Why? Because you have QL. So your thermal efficiency should be less than 100%. Please understand why. Why we have this QL. Don't say that because our device is not ideal. Don't say that because you don't have ideal materials. Don't say because you have heat losses and dissipation. No. All I mentioned, it's true. But it's because you don't know how to avoid it. You know, theoretically speaking, you may avoid dissipation. Theoretically speaking, you may have absolutely adiabatic system without heat losses. Theoretically speaking, you may have ideal material. But still, your efficiency should be less than 100% because QL cannot be zero. Not because you don't know how to do it, but because of the second law. Okay? That's why your efficiency is less than 100%. Okay? You may say, so how big is it? Let's say 95, 99, 20. I will tell you later. We will derive it. It will be some limitation because your best system is when you pay less penalty, right? So we will discuss it. So let's say I have device like this on the right. You see, I have furnace which heats my heat engine and give to my heat engine 100 megajoule. And 55 megajoule of it will be converted into work. So what is efficiency of this device? And how much will be lost? 45 will be lost. You should understand that 55 plus 45 give you 100. Otherwise, you violate energy. So, what is the efficiency of this device? Yeah, definitely. 55% definitely. Because it's desired over required. Work output, all this. And 45% will be lost. Why? Because you have the second reservoir. It cannot be like this. It cannot be, right? It cannot be like this. It should exist. So here, if you have what you see here, if you have two devices, here, let's say I have two heat engines, 1 and 2. They have the same source and the same sink, okay? And heat engine 1, both of them get 100 kilojoules from the source. But first heat engine had output of 20 kilojoules. So what, and 80 kilojoules will be lost then, right? So what is efficiency of first one? It's 20%, right? And let's say I have another heat engine. It gets 100 kilojoules, but it converts 30 of them into work, and 70 will be lost. So what is efficiency then? It's 30%. Does it make sense for you? Everybody understands this? Okay, great. And which one is better? So second is better, right? Okay. So does it make sense? So do you understand now what is thermal efficiency, what is heat engine, and what is Kelvin-Plank statement? In other words, it says that your heat engine cannot have one reservoir. System cannot operate in a cycle with one thermal reservoir. You should have two reservoirs. That's a must. So now people may ask, okay, so this QL goes out. Can we utilize it somehow? Let's say, can we save Q out? Well, answer, so people try. For instance, it's classical example, if you have power plant, if you have some factory, if you have electric power plant, this heat which goes to second reservoir, people try to typically to use this for heating housing. If there are apartments near power plant when workers live, typically they want to heat it. But in fact, what you do here, you just extend your system. So yes, you can use part of this QL, that's okay. But if you consider the system, your factory plus apartments, still something will go to the environment. It's impossible to avoid it. No system can operate with one thermal reservoir. You should lose some heat. So unfortunately, total answer is no. You cannot save entirely Q out. Q out will be there. You may change Q out when you change your system, but it's something should be lost. It's secondly. Okay, no questions about Kelvin-Plank statement? Then we have 10 more minutes, so we'll start something else. And let's forget about, so you understand that power cycle does only one thing that ancient Greeks did not know. It converts heat into work. There is something else we have in our homes that ancient Greeks did not know, and that is refrigerator. So what is typical refrigerator or heat pump. Idea actually behind them is very similar. This is a device which transfers heat from cold to hot source. How it looks like. So that is example. So for instance, and you see, so if what you see here, it's actually opposite to power plant. So here the cycle goes counterclockwise. So work done here will be negative. Here work is done on the system, it's done by a compressor. So how it typically works? Let's say you have a refrigerator. So in your refrigerator, you have Freon which flies here. And first of all, you have evaporator. So what happens in evaporator? In evaporator, your substance evaporates, so it takes latent energy, it consumes latent energy from environment when you evaporate, right? It becomes vapor. So here you take heat from your fridge, and then you task it to put it into your kitchen. How to do it? Here you have compressor, and when you compress the substance, its enthalpy goes up, work is negative from your point of view, so enthalpy is higher, and then it condenses. When it condenses, what happens when it condenses? You release heat, and this heat goes into your kitchen, to environment. So you need this. And to connect it, to make a cycle, you have expansion valve. What happened in expansion valve? Remember, you reduce pressure to reduce temperature. From room temperature, let's say 30 degrees Celsius, to fridge temperature of minus 25. We discussed it in chapter 5, right? And we discussed that if it was ideal gas would not see expansion valve. That's why we use Freon, something really not ideal. That really have throttling process here, right? That's why we can use Freon or water, but not ideal gas. If there was no expansion valve, fridge would not work, right? But there is another important point here. There is compressor, right? If there was no compressor, evaporator and condenser would not be connected. That is fridge cycle, classical fridge cycle. And I tell you that heat pump is very similar. The only difference that in fridge cycle, it's actually the same device how it works. But in fridge, what you do? You transfer heat from your fridge, from your inside part of the fridge into the kitchen. You don't care about the kitchen here. Kitchen is your hot source now, which you don't care about. You care about your fridge. When you had heat pump, it's a little bit different. In heat pump, you transfer heat from the street from outdoor to indoor. You take heat from the street into your house, and then you don't care about the street. Then QL goes from the street, but you care about QH which goes in. But otherwise, it's the same device. Okay. And now I will tell you about Clausius statement. Clausius statement is very simple. It tells you that you must have compressor, or otherwise it tells you that your fridge or heat pump does not work for free. Okay? You need to deposit work. If I turn on my, like my son also knows that if I turn off electricity, my fridge would not work, right? But I tell you something that he does not know. It's because of the second law. It's Clausius statement, which roughly speaking says that your fridge exists, but it cannot work for free. You need to deposit the work. Otherwise, this is Clausius statement of the second law. Strictly speaking, it says, read here. And remember, it's serious. It is impossible for any system to operate in such a manner, such a way, that the sole result would be energy transfer by heat from a cold to hot body. Here, please understand, sole result is important. So, it means that heat goes directly from hot to cold source for free, right? If I have hot cup of coffee, it will get colder because it goes to equilibrium. And if it was Aristotle here, he would tell you vice versa may not happen. Go to Mount Olympus to take snow. Heat cannot go from cold to hot source. But you are smarter. Please, when you have exam 3 in a month, less than a month, if you have don't write me that it is impossible to transfer heat from cold to hot source. It's wrong. Your fridge does it. It is impossible to do it for free. You need to deposit some work input here. You should connect your fridge to electrical power supplies. You need compressor to work. It is impossible to do it such that sole result would be this transfer. If this is not sole result, it's possible. So, otherwise it states that your fridge might exist, but it does not work for free. You need to deposit something, right? Here it is. It cannot be, as you see here, it cannot be like this. You need to deposit some work input. That's a must. This work input cannot be zero. You may, so how big is it? Later we will quantify it. We will discuss minimal theoretical performance, minimal, because this is penalty you pay, right? The God or the nature told you don't transfer heat from cold to hot source. But you say, I want this. I want to use fridge. And they tell you, okay, but then you will pay penalty. And here you will see what penalty is. QL is not equal to QH. So that will be your penalty. Does it make sense? What is Clausius' statement? Now, when we talk about refrigerator and heat pump, we don't talk about thermal efficiency, but we talk about COP, coefficient of performance. What is it? Again, idea and definition is the same. Desired over required. If I have, let's say you have your refrigerator. When you buy refrigerator, what do you desire? Why do you need it? What do you want from your refrigerator? You want heat to be taken out from your food, from your fridge, from your environment, from your enclosure, right? That is what you require. But that is what you desired, that you want. What do you must to have? What do you require? As you know from second law, you require some work input. Your fridge should be connected to power source. So you require this. That was your desire, that is what you required. And now you know that what is required cannot be zero. So your coefficient of performance is finite. It cannot go to infinity, desired over required. Does it make sense? Now, let me ask you, unlike thermal efficiency, so remember thermal efficiency should be less than 1. But this value cannot be larger than 1. The answer is yes. Because please understand what is fridge actually. It's here you don't convert heat into work, vice versa. This is like transferring. So your fridge, it's like a cart. It's like a cart which brings heat upstairs. So imagine I have heavy loading. I have many bricks which weigh 1 ton. And I want to bring them to 10th floor. Can I do it? Potentially, yes. If I have a good cart, I will go to elevator, I will put it and put up. And they weigh 1 ton, but I weigh, let's say, 50 kilograms. So they weigh 20 times more than me. So in that sense, coefficient of performance will be 20. I am able to bring it. And like when there are small insects like ants, for instance, you know, ant can load the mass 20 times more than the ant. They're very efficient. So that it is. It's okay to deliver something which weighs much more than you weight. It's okay. So your coefficient of performance may be larger than 1. But it cannot be infinity, because if I am not existing, who will put it up? Nobody will put it up, right? Nobody will put it up. So definitely this value is finite. It cannot be 0. Okay? Does it make sense? Yes. For coefficient of performance can be, for refrigeration, a very good question. So for refrigeration cycle, coefficient of performance can be less than 1, can be larger than 1, can be equal to 1. Whatever, it depends. It depends on the system. But there will be some limitation. It should be less. It's a very good question. It should be less than some COP maximal. Okay? And this maximal value, we will discuss later what it is. It will be formula for this. Okay? Now, for refrigeration cycle, for heat pump, it's very similar. I told you what heat pump does. It's the same cycle, but heat pump takes heat from the street and transfer it to your room, to your house. Now, what do here it's the same, but a little bit different. Because now, what do you desire? Now you don't care about your street, right? You care about your house. So that is what you desire. But still, what you require what goes in. So now your coefficient of performance, it will be this. That will be your coefficient of performance. And again, it will be not infinite, but it will be finite. But you will have this formula. So coefficient of performance of heat pump is actually larger than coefficient of performance of fridge. So coefficient of performance of heat pump will definitely be larger than 1. Okay? And again, later we describe what is the finite value for this. Okay, that it is. So please, I will stop at this point. We are ending, but you should, we are starting this, we will continue on Wednesday. But what you should realize? Realize very basics of second law, something that rules an H in addition to first law. It's difficult. There are various statements. Please remember what is heat engine, which operate over power cycle. Okay, what is heat engine? This is heat engine. And please understand that how Kelvin-Plank statement looks like. It states that heat engine cannot have 100% efficiency. Why? Because it cannot operate with one thermal reservoir. You should have another thermal reservoir to lose something. And the same for, we know that there is refrigeration cycle and heat pump cycle, which transfer heat from cold to hot source. And there is Clausius statement, which says that it cannot work for free. You need to deposit some work input to make it feasible. And later we will show that these two statements are equivalent. Either they are violated both, which is impossible, or work together, which is true. Okay, I will stop at this point, and please ask your questions, and please take it seriously. It's an important topic. It will not be at your exam too, but it's still very important after this. And we will continue on Wednesday. I will see you on Wednesday.